That's why the people use exponential smoothing more widely used. Simple moving average or exponential smoothing. So exponential smoothing, even though this one has this kind of formula, that's why this is exponential smoothing. Actually, has a same idea with the weighted moving average. Okay. So this is what our new forecast of the time is the just previous number plus alpha times of the previous error. This is the error at time t minus 1. So previously we know what was the forecast, and what was the error, because of what was the actual, I know. So you calculated the error. So my forecast was smaller than the actual, then you have to increase your forecast, right? So I will bring the previous forecast, and then since my previous forecast was less than the actual, so I will add a positive number here. So I will increase my forecast. If my previous forecast was overestimate, if previous f is greater than a, then you're gonna have a minus here, so you are lowering your forecasting. That's the idea of the exponential smoothing. But why I say the exponential smoothing is the same as the weighted moving average, that's because if you take a look at it here, this let's say F12 is the period we're trying to forecast. So F12 will be, so originally this was like what, F11 plus alpha and then A11 minus F11, right? That's the our original formula, definition of exponential smoothing. But since we have F1, F11 here, so if you just expand, then you will have a alpha A11, and then this one is what is 1 times F11 plus alpha minus alpha times F1. So you can make it is 1 minus alpha F11. Right, that's how it becomes this one. So basically it's from here. And we substitute the F11 because the F11 will be the same way using the actual tenth one, because the 11th forecasting what we use the 10th period information. So you just replace this F1 with this one. Then you will get a F2 will be this number, and then instead of so I will show you. So if you just replace it, F12 will be what? This is alpha 1 1, and then if you replace it, this will be 1 minus alpha times A10 plus 1 minus alpha F10, right? Here. So if you just expand it, this is alpha A11 plus, this will be the alpha times 1 minus alpha A10 plus 1 minus alpha square F10. And if you keep doing that, replacing F10 to the using F10 equals the alpha times A9 plus 1 minus alpha times square and F9, right? And you're replacing and replacing and replacing, then eventually what you will have is F2 is alpha times A11, alpha times 1 minus alpha times A10, alpha times 1 minus alpha square times A9, and so on. So this is all past actual data and a different weight. This is a different weight. Weight 1, this is a weight 2, this is weight 3. Since alpha, you have to choose between 0 and 1. Multiplying alpha times 1 minus alpha will be smaller than alpha. So this weight is keep decreasing. As you multiply more and more 1 minus alpha, this is keep decreasing. Okay, so this is the same way. As a result, what you have is you are having weighted average. It doesn't have a time span because it's keep going up and then going up to the A1, the first data. And then we give a higher weight on the new data, and we give a really low weight for the old data. So as the data is getting older and older, we will have a smaller weight, smaller and smaller weight. So older information get exponentially less weight. So this is the idea of the same idea with the weighted moving average. However, the weight is calculating this way. So how many number do I have to decide? It's one number, which is alpha. Depending on the how much smooth out you want, you just choose alpha. Then automatically all the weight, the past data, weight for the past data is automatically calculated. So that's why the people use exponential smoothing more than the weighted moving average. Weighted moving average can be useful when you have some specific requirement. However, that is going to be pretty tedious because you have to decide so many different weight if you don't have any idea. But exponential smoothing capture the idea of the weighted moving average. I'm going to give a high weight for the newer data and then smaller weight for the old data. However, here the practically easy to apply because I have to decide only one number, which is alpha. So if you choose a small alpha, then what will happen is this will be so this is like that. If the demand is stable, you don't want to overreact to the change. That is really just short-time variation. So you want to make it less sensitive. Or if demand is really changing rapidly, we want to react quickly as possible. So this is a more sensitive. So high alpha means we're gonna give a high weight for the newer data, right? Low alpha means I don't give a too high. Still, newer data has a higher weight than the old data. Okay, doesn't matter what alpha you use. Still, the newest data has the highest weight. However, compared to the old data, this is not that great, that much high. But if you use a high alpha, which means I'm giving a really high weight for the newer data, and I'm giving really low weight for the old data. So that's why this one will move more sensitively. So something change, and your forecasting catch up pretty quickly. But if you use a low alpha, because you give up some significant weight to the old data, it will not react that fast. It's less sensitive. So you should be able to see the actual examples here. So moving average with 3 period, you calculated the past 3 data. Why I don't calculate this one here? Because I can use only the past data. So when you make this forecast for this fourth period, I can use only past 3 data, right? So calculate the average of this one, and then you calculate it. This is the average of these 3 numbers. Exponential smoothing. Exponential smoothing, first number is just first number. Why the first number is first number? Because the exponential smoothing f2 is alpha times no, f, actually this should be f1 plus alpha times a1 minus f1. So F2 I can calculate it, but F1 I don't have a F0, right? I don't have a A0 here. So this one you cannot calculate it for the F1. So we just use F1 because F1 you cannot calculate it. F1 is just A1. Okay, the second one is we use the first one. As you can see, the first one I use the actual number. So this is not, maybe when you evaluate your forecasting, you should take it out, this one. You should exclude this one because I cheated. I use F1 as A1. I use A1 to make a forecast F1, which means the first period my forecast was exact. But that's not true. I mean, because I have to start the exponential smoothing, that's why I just forced to use F1 was A1. However, that's a kind of cheating. But without cheating, we cannot start the exponential smoothing. And second one is I'm using the past data, and then the past data was 0. So this is also, however, this is wrong. But these two numbers should be the same. These two numbers should be the same. Doesn't matter what alpha you use. However, this can be wrong, so you can use the second period, starting the second period. So first period, you should exclude this for evaluation. Yeah. I'm pretty bad at the spelling. But when you have like hundreds of the data, then you don't have to exclude it because just having a one number, cheated one number, that doesn't change your accuracy that much. But when you have just few, then you should exclude the first one because this is kind of cheating, right? And then as you can see, if you use a 0.5, as our data is keep going up, so this one also catching up pretty fast. This 700 appears here. However, if you use a small alpha, this is not going up that fast. 700 happens here. So this one is less sensitive to the actual number change. This is more sensitive to the actual number change. But still, moving average or smoothing method, there is always a lag. As you can see, the actual 700 appears from here, but only 700 appears like a 2 period later. And this one is, I don't know how many periods later. So it takes time to catch up. So if you draw the graph here, then you can see moving average 3 is the yellow one. So this blue line is the actual sales, right? And yellow one is moving average. Again, my demand, my sales is jumping up at the period 3 to 4, but my moving average jumping up after period 4. So this is a time lag. And the green one is the when exponential smoothing using the alpha is 0.5 is pretty similar to the moving average 3. Even though there is a lag is catching up, but when we use a smaller alpha, it's less sensitive. So even though my demand, my sales is jumping up, it's just smoothly going up pretty late. So how much you want to smooth out? Actually, this is a way smoother than this one because it's still has a fluctuation, but actual data has more. So how much you want to smooth? As you make it smooth, actually your smoothing method has a time lag. It's less sensitive to the change of the actual number.